Hey guys, in this video we're going to go through an optimization problem, one that involves a cylinder as you can see here. And we're not only going to solve it, but we're going to discuss what a critical point is, how to use the first, how to use the second derivative test to actually assess whether we got a max or a min. Given that the way that we find maxes and mins is the same, we take the first derivative and make it equal to 0. So there's got to be a way to distinguish whether you got a max or a min. And this is a typical exercise which involves a volume. So let's go through it. And by the way, while we do it, we're going to go through our cheat sheets, as you can see in the screen right here, that we developed over the last few lessons or over the last few videos. So we're going to understand the problems, create a sketch, attribute variables, all these things. We're going to do them one after the other. So let's get to it. And before I forget, I swear this is the last thing. You can see you can download the exercise list for optimization problems for IB Math in the description of this video. So right now, let's tackle the exercise. We have a cylindrical can without a lid, which is to be made to hold a volume of V centimeters cubed. Now, do notice that despite the fact that we don't have a number associated to it, V, capital V, is a constant. The radius of the base is r and the height is h, as shown in the diagram right here. First of all, we're going to show that h is equal to v over pi r squared. Now, this is a simple exercise, one that if it was found in an IB exam, you would be something like 1 or at most 2 marks, probably 1 mark only. If we go through our cheat sheet, we can see that the sketch was already created, it was already given. We can already answer a few questions such as what was given. Well, we were given the volume. The variables that we're going to use are r and h, which is mentioned right here in step number 3. Also, going back to the problem, what do we need to optimize for? Well, we are going to find the value of the radius that minimizes the surface area, which is yet to be found. So another variable that was given, it was mentioned, is capital A, which is the surface area. Do notice that the cylinder does not contain a lid, meaning there's nothing over here. Therefore, the total external surface area is only composed of the base and the curved surface. But let's go back to question A, which is to find the volume or actually to find h as a function of r, analyzing what the volume is. What is the volume? The volume is the area of the base times the height. The base of the cylinder is pi r squared, and the height is h, which is this one. So pi r squared times h is equal to capital V, meaning that h can be rewritten as v over pi r squared. And there we go. This is question A. Now for question B, let's analyze what is this total external surface area. We have the area of the base, which we know to be pi r squared, so nothing changes. And we need to add to this curved surface. If you cut this can over here and you open it, where you're going to form is a rectangle where the height is h and the base is this circumference right here, which is 2 pi r. Therefore, the curved surface area is equal to h times 2 pi r. And there's no lid. Therefore, this is the total external surface. Now, do notice that this is a function of r and h, which is a problem, not only because he mentioned that we need to write it as a function of r only, but also because we can only differentiate these models, these functions, when they are written as a function of one variable only. So we're going to convert h to r using item A. We are going to substitute h over here, and that is going to give us pi r squared plus v over pi r squared times 2 pi r as the surface area as a function of r only. There are variables and constants to simplify. We can simplify an r over here and over here, simplify pi. Therefore, a as a function of r only is equal to pi r squared plus 2v over r. Now, question A is done and question B is done as well. And do notice that in our cheat sheet, we already know, for example, what we need to optimize for. So we're going to minimize the surface area, which is what we're going to do next. The restriction that we had was the volume. We have a finite volume, which was capital V. And we already defined the function to be optimized in question B. And we did write it in terms of one variable only. So right now we're going to tackle item 6, or step number 6, which is to find the critical points of the function being optimized given that a critical point or a critical number is a number in the domain of f such that the derivative is equal to 0. It's actually whether the derivative is equal to 0 or it does not exist, but for IB math, it's where, for all purposes, it's where the derivative is equal to 0. That's how we're going to find the maxes and mins, the points, the candidates for maxes and mins. Now, what is our function? It's a of r, therefore the derivative of a, and by the way, keep in mind that the variable is r, it's not v or pi. It is equal to pi times 2r plus 2v times, given that we can rewrite this as 2v r to the negative 1, it's 2v negative 1 r to the negative 2. Which means that a prime of r is 2 pi r minus 2v over r squared. We're going to take this derivative, make it equal to 0, and find the critical point. So 2 pi r minus 2v over r squared, it's equal to 0. Therefore, we have 2 pi r equal to 2v over r squared. We can simplify the 2's and cross-multiply the r squared from the denominator of the right-hand side to the left-hand side. So we have pi r cubed equal to v, which means that r cubed is equal to v over pi. Therefore, r is equal to the cube root, which is a beautiful answer, v, the cube root of v over pi. So this is the critical point. Now, the million-dollar question is this a max or a min? Did we actually get a min or a critical point which generates a minimum surface area? And in order to assess that, we need to use the first or the second derivative test. For this specific exercise, given that finding the second derivative is not that tricky, it's actually fine, it makes more sense to use the second derivative test, which means that we're going to differentiate a of r again, and we're going to replace that critical point into the second derivative. If we get a positive result, we have a min. If we get a negative result in that substitution, then we have a max. So right now we're using the first or the second derivative test to prove that we found a max or a min. In this case, as mentioned before, we are going to use the second derivative test. Now, what is a prime prime of r? Given that this is a prime of r, which by the way can be rewritten as 2 pi r minus 2v r to the negative 2, we have the second derivative as 2 pi minus 2v times negative 2 r to the negative 3, which can be rewritten as 2 pi plus 4v over r cubed. Now we're going to take our critical point c and plug it into the second derivative. If we get a positive result, then we have a minimum. If we get a negative result, we have a maximum. So the question is, what is a prime prime of the critical point, the cube root of v over pi? It is equal to 2 pi plus, and do notice that we're plugging it over here, plus 4v over the cube root of v over pi cubed. We can simplify the cube root with the cube, which means that we get 2 pi plus 4v over v over pi, which is 6 pi, which is positive. Therefore, we do have a min. Now, what is the main meaning of that? It means that if we take this value of radius and we use it to manufacture this can, we're going to get a can which has the minimum possible surface area. And that is it. We just proved that we got a min. Now, questions that the exercise may ask you, for example, what is the height of this can? In order to find that, you can just replace r over here and find the height. Or the exercise might ask you, what is this minimum area? Then in that case, you would replace the cube root of v over pi over here and find this minimum surface area. And that's it.